Well, we're going to continue on now going through this type 130 LC meter. In part 1, we looked at it just fresh out of the box and saw some of the issues inside. In part 2, we cleaned it up and showed that it functioned, and that it functions better on the lower scales than the higher scales after replacing some tired or dysfunctional vacuum tubes. And in part 3, we're going to start going through this and seeing how the individual components have aged in an attempt to get it to function correctly on all the scales. So let's jump into this. The manual is available online. When I say the manual, it's a bit of a moving target because there are at least 2 versions of the manual available for different production runs. So I'm going to show a portion of the schematic here that we're going to start with. There are 9 paper tubular capacitors in this instrument, and in anything that has paper capacitors, paper wax capacitors, paper tubular capacitors from the 1950s, 1960s era, you should immediately go to those and check them because they almost certainly will be leaky. Now, it is true that Tektronix used the best components available at the time. So, for example, I would not expect to find many drifted resistors. But paper capacitors are paper capacitors are paper capacitors, and they're all suspect. So what I've shown here are a series of capacitors. This one is actually a mica capacitor, C90. But C91 through 94 are paper tubulars. The reason I'm showing those on the schematic, and we're going to look at those first and test them for value and leakage, is that they're connected on one side to a plate of a tube and to some other nodes in the circuit. But on the other side, they're connected to nothing if the value switch or the range switch is in the off position. So the point is we don't actually have to take these out of circuit to test them, which is a happy thing. Moreover, these capacitors are particularly easy to get to. They're just right here. So this one is the C94, 93, 92, 91, and then here is 90. In the next shot, we'll get the DE5000 LCR meter, and we're going to test a couple of these capacitors to see what the values are, 5-6 decades later, and then we will leakage test them with the Heathkit LCR bridge. Okay, so here's the favored DE5000 little meter, which I just absolutely love. And what we're going to do is we're going to test this mica capacitor first. So there are the clips. I've already made sure that it's zeroed and calibrated and all that. And let me just move this a bit so that we don't get as much reflection. Alright, so this is C90, and C90 should weigh in at 250 picofarad. And you see that it is a very close 260 something picofarad. Alright, now C90 in the manual, let's look this up in real time, is listed at plus or minus 5%. So what's 5% of 250 picofarad? It's 12 picofarads, 12 and a half. So this is right on the edge of specification. I'm not going to change it because there's extraordinarily low probability that this leaks. We'll test that in a moment. And this is probably close enough. However, let's look now at C91. See how that goes. So this should weigh in 0.0015, which would be 1.5 nanofarads. And you see that this is not at all close. So it's got to go. Let's look at this. This is C92. It should be 0.0047 microfarad or 4.7 nanofarad. So that's not close. Let's go to the Sprague capacitor that should be 0.015 or 15 nanofarad, and you see that that's closer in value. That's 19 instead of 15. And then finally, this might be a little bit challenging. Let's look at what should be 0.047 microfarad or 47 nanofarad, and we see that it's 55, so that's pretty far out as well. Now let's do a leakage test. I suspect what we will see is that all of these capacitors, except for the mica capacitor, will fail miserably. So here we've got the Heathkit capacitance bridge, and I'm going to hook up C90. All right. Now, C90 is listed at 500 volts. So if we see leakage at anything less than 500 volts, then we should be suspicious. Okay. Here's 6 volts, 10 volts. I'm just going to keep going up. The eye is wide open. It's not even blinking when I change. There's 500 volts. Not even a hint of a leak. And I'm just going to stop there. That mica capacitor, that's in good shape. Now, I think we are likely to see abysmal performance. So this is C51. This is 400 volts. So this should show an open eye up to 400 volts. So put it on leakage. Okay. So there's 3 volts, good. 6 volts, all right. 10 volts, 15 volts, okay. 25 volt, really squinted. If I go up to 50 volts, that'll be all, yep. So it leaks at 1/8 of what it should. It leaks at 50 volts. 400 volts is just going to be hopeless. So that one's got to go. Let's move on to the next one here. This is C92. All the rest of them should be 400 volts. Good to 400 volts. Put it on leakage now. Notice how it's squinted at 6 volts. And 10, 15, it leaks at 15 volts. And this is typical of these Bumblebee, Black Beauty. I think they go by many names, but these types of capacitors are notorious for leaking at very low voltages after several decades of service. All right, well, I'm not going to belabor the point. Maybe just do one more. This should also be 400 volts. The point is that these sorts of tubular capacitors are always suspect, even if they were very high quality when installed in late 50s, early 60s. So this one leaks at 25 volts. So you get the picture. So the next thing that we should do, having resolved to replace all those capacitors, so that's going to be 1, 2, 3, 4, 5, 6, 7, and then the other ones, zoom in a little bit, are going to be real bears to get at. Here is 8 right there, and then 9 is, let's see if I can shine a light on it to point it out a little bit better. So it's right back in there between those two switch arms in the switch assembly. So in order to get to those, I'm actually going to have to remove the entire face assembly and switch assembly to get in there, and that's going to be, the technical term is a royal pain. Off camera, I I spot checked a few of these resistors. I was particularly worried about the resistors because carbon composition resistors are notorious for drifting, and they usually drift higher in value. I haven't checked all of them, but I spot checked half a dozen. And out of those half a dozen, I found that one had drifted slightly out of tolerance. So I need to go through and maybe do a bit more of a random audit. But the resistors seem to be in pretty good shape. So I think the plan is for me to replace the tubular capacitors, the paper capacitors in here that I've either verified leak or have an extreme high probability of leaking, and so that's 9 capacitors. And then I think I'm going to turn it on and test it out again and see if I've improved the performance on those scales. I also need to go through and look at the waveforms and see if those improve when I bring the capacitors back into specification. So there's quite a bit more to go on this. Alright, pardon the fact that I'm holding this with my hand, and so you'll see some motion. I'm not using the tripod. But I'm starting to replace these capacitors by first desoldering the old capacitors and removing them. And one of the things that I did not talk about earlier was a capacitor can, which is visible from the other side of the chassis and is visible, the contacts are visible, the leads are visible from this side. So I'm just going to zoom in here. You can see them the contacts pretty well. Alright. And so this is the underside of that capacitor. And I want to point out here, and to a lesser extent here, actually to about the same extent. So there and there you can see corrosion. Material that has leaked out, electrolyte that has leaked out of that electrolytic capacitor can. And so that just goes to show that the electrolytic filter capacitors have got to be replaced as well. I've completed the repairs on the Type 130 LC meter and actually managed to calibrate the unit to a good enough level. And so it's probably useful to run through what I did and show that the meter actually operates now. So what we're going to do is look at what I did. There were 9 tubular capacitors that we replaced. We demonstrated the leakage on several of the capacitors that were in this row. And you'll notice that I have replaced those capacitors with what I had on hand. This is a little bit ugly. Let me zoom in here. Okay. So these are the capacitors. They're C91 through C94, right through here. 91, 92, 93, 94. And as I said, these were just capacitors that I had on hand. The rationale of using just any old thing that I had on hand was that these started off life as paper capacitors, and almost any modern capacitor within reason would have better characteristics than they had at the beginning of their lifetimes. That may or may not be true, but I think it's true. And the fact that I was able to get this back into operation so easily suggests that perhaps it is true. But anyway, I replaced those capacitors, those 9 capacitors. Here's another one up here. And there were 2 that I replaced that were really difficult. So one was down here, as I pointed out earlier, and another one was back behind this switch assembly. Now earlier I said that I was going to have to, take off this entire front panel to get to that. What I decided to do when I looked at how it was connected, I actually decided to mount it on the other side of this chassis. So it's on the opposite side with the vacuum tubes. And I have a wire that just attaches to this tube down here and goes up through this space here by the meter assembly and attaches to the capacitor, which then goes to, I believe, the guard voltage outlet on the other side. It's a bit of a kludge, there's no two ways about it. As I said, I am aiming to restore this to functional status, not to factory state. I might at some point get tired of that and try to mount the capacitor where it should properly go. A couple of things before we go to the other side. I had never soldered with onto these ceramic clips. I found it to be very difficult, and in fact a couple of really bad things happened when I was soldering. I thought I was being clever. I read the manual and I reduced the heat that I normally solder with, and for whatever reason wasn't making good thermal contact with the silver rails, and I found it difficult to unsolder and then solder. I have a fairly narrow chisel tip, so I was able to get into these, and I thought that would help make good thermal contact. Really dumb idea. Really dumb idea. The problem with that idea, as I found out, is that you tend to put tension perpendicular to the inlet there, and if you put tension on that, that is then transmitted to the ceramic, and it's really easy to crack the ceramic rail. And in fact, I did crack one down here. This video channel will always show the good, the bad, and the ugly. Here, let me see if I can just arrange this so that you can see. Wow, it's going to be difficult. Suffice it to say that I cracked this porcelain assembly. It wasn't catastrophic. I was able to shore it up with some glue, and I sulked the rest of the day. The other thing that I did was, when you are soldering at the ends of these porcelain strips, the ends obviously now are very fragile. They're more fragile than the inlets in the center. And I actually broke off the corner of this right here when I was desoldering the old capacitor there. Again, I was able to shore that up with some glue, and we'll see how that lasts with heating and reheating and so on and so forth. But suffice it to say that this was a very humbling experience. I felt like I was a freshman in high school learning to solder again. It was very bad. I'll get over it. But if you're going to do this, be very careful. And I should say in general, if you are trying to do any sort of repairs in this meter, there are high voltages inside, and you are doing so at your own risk. If you don't know what you're doing with high voltages, please don't try to make these sorts of repairs. Alright, the resistors, as it turned out, I alluded to this earlier, are actually remarkably accurate for their age. Most of the resistors read bang on. There were a couple that were at the edge of specifications. I tended not to replace those. I did replace this resistor here. Upon closer inspection, it had actually cracked. Let's look at the flip side, and there was another surprise over there, which we'll get to shortly. Okay, zoom out a little bit here. All right. So the surprise that I found was this tube right here, which is very clearly labeled A6U8. We'll zoom in on that. All right. This was clearly labeled a 6U8. In fact, had a tube in it that was a 6GH8. Now, both the 6U8 and the 6GH8 are versions of the same tube. They are not identical tubes, but they're both listed in the receiving tube manual as medium mu triode and sharp cutoff pentode tubes. So they have the same pinouts, so this is why something bad didn't happen when I had plugged it in before. And I'm frankly surprised that I missed that on my earlier inspection. You recall I took all the tubes out, I dusted them off, and I tested all of them. But what I overlooked in this case was that the tube, as it was labeled, was not the tube that was called for on the labeling on the chassis. So you have to be careful. You can't take anything for granted, and you just have to be absolutely maddeningly methodical when you go about looking at old pieces of equipment. So I swapped that out for the correct tube, and you'll see the results. All right, so this is the kludge right here. This capacitor goes down and in fact attaches to the guard voltage outlet, and you can see what I've done. I've just got that wire going up through that hole there. It's not pretty. You could say it's just kind of hanging out there flopping in the breeze, but it's not really flopping in the breeze. I used solid wire to attach it. It's not going anywhere. It's solid. It's not going to bump up against the chassis or anything else. But I might, affix that solidly at some point in the future. All right, the other notable thing that I did is I replaced the can filter cap. You'll recall that, this is what I removed. Here, let me show this a little bit better here. So zoom in. All right. So this was, you can see right through there. That's all oxidation, and there's more oxidation. And this is stuff that had come down out of the capacitor. This literally chemically leaked. And it's not surprising for capacitor of this age. This is, I had 15 microfarad at 350 volt capacitors in stock, and so what I did was I mounted those two like that. The negative leads of the capacitors I wound together and soldered together, and then just attached. I soldered them to the mount, which was screwed to the chassis. Verified that the puddle of solder made very good contact, electrical contact and mechanical contact with that plate, and so that's how that worked. And then I took the positive end of the capacitors and attached those to the parts of the circuit to which they needed attached. I also tested on an oscilloscope measured the ripple voltage on my fix, and was able to show that after you do the calculation on the magnitude of the ripple on top of the voltage that it's delivering, that it was less than 0.6% ripple. So I think that's pretty good. I went through the manual and walked through the calibration procedure as closely as I could. Part of the procedure included looking at waveforms at different stages of the circuit on an oscilloscope, which I did, and verified that those were symmetrical and had the correct waveform. Some of that was verifying and adjusting the frequency of the fixed oscillator, the 140 kilohertz oscillator, which I did. And then the actual calibration procedure for the levels, the meter readings, use something called a delta standard that Tektronix sold, and these are available online through auction sites and so on. And I don't have one of those, so what I did was I made my own standards for inductance and capacitance with inductors and capacitors that I had on hand and that I could measure with my DE 5000 LCR meter. So this is not a rigorously calibrated unit, This is an approximately calibrated unit that I think is good enough for day-to-day bench use. Let's now look at that and see how well it performs. We've got this set on the 300 picofarad scale. I don't have the mount, the component mount that came with this meter. Perhaps at some point in the future I will snag one of those if I can find them, or I'll try to fabricate something. So for now, what we're going to do is we're going to use this alligator clip. And this right here is a 250 picofarad capacitor. And so I'm going to, so this is zeroed, there's no pulsations or anything like that. I'm going to touch this here. You see I'm reading just a hair over 250, maybe call it 255 picofarad. So that's that. Off to the side here, I'm going to measure what this is on the DE5000, and I'm going to do it at the 100 kilohertz reading on the DE5000, because that's as close to the 140 kilohertz oscillator that this uses. And in fact, I'll just hold this over here, I'm reading 257 picofarad. So that's pretty good. 257 versus what I approximate as 255 on the scale. Why don't we zoom in just a little bit here to make this a little bit easier to read. All right, so that was 250. I don't have a 300 picofarad capacitor, but I have a 200 picofarad capacitor and a 100, which I can just mount in parallel. And let me do this here in a way that hopefully will not be too bad. All right, so what I've done here, just so you can see, so I've done that. It's ugly, but it should be near 300 picofarad. And I'm going to, and so what you see is I'm actually pegging the meter, so I'm over 300 picofarad. Now let's see what the DE5000 reads. And in fact, I'm over 300 picofarad. I'm right at 303 picofarad according to the DE5000. Now let's look at the 200 picofarad capacitor now. And I'm reading 200 right on the nose. And the DE5000 reading of that is just under 202. So pretty good. Let's look at the 100 picofarad capacitor. Reading just a hair under 100. And the DE5000 reading just a hair under 100. I could be more scientific about this and look at percent accuracy of, percent of full scale readings and things like that. But I don't want to do that right now, and I just want to demonstrate that this is working, and it's working pretty well. Okay, before I go on to the next capacitor, why don't we change ranges? We'll stick with the 100 picofarad capacitor. Now let's go down to the 100 range. You can see that this is still zeroed and it's not pulsating, so we're good to go. So let's now look at the 100 picofarad, and in fact you see that it's probably somewhere around, well, between 95 and 100. So we could call that 97 or 98. Very accurate. Let's look at, well, let's guess what this is. Looks like it's somewhere around 68, so maybe 70 picofarad capacitor. And in fact, it is labeled as 70. Let's see what the DE5000 says. That says it's 69. Not too shabby. All right, let's go and figure out what this capacitor is. That looks like it says very close to 20, so we'll call that a 20 picofarad capacitor. And in fact, that's what it's labeled. And what the DE5000 says, 19.6. All right. Let's go down now to the 30 picofarad scale. And you see that I need to adjust this just a hair. All right. It's wiggling just a tad. All right. So let's see what this 20 picofarad capacitor reads on the 30 scale, and it's just a hair under 20. Outstanding. All right. Why don't we get now down to fairly small range. This capacitor now reads on the 30 scale 7. And in fact, it's labeled as 7. And the DE5000 reads 6.9. Now, any lower than this, and I'm expecting that my less than high-tech leads are going to start adding stray capacitance. But let's stick with the 7 picofarad capacitor, and on the 10 scale, it's reading just a hair under 7. It's very gratifying. And now let's look at this capacitor. This is a 3 picofarad capacitor. All right, and on the 10 scale, I'm reading about 3.5. All right. Let's see what the DE5000 reads. Now, I'm just doing this with the Kelvin clips, and I'm reading about 3.5. That's just really astounding. There's 3.5. Now, let's now look at the Kelvin clips where I still have my alligator clip in the circuit. And so yeah, you see it's starting to fall apart now. Now it's 4. So I've added what, half a picofarad capacitance just with the alligator clip. Right. So the point is that they're, you know, at the low capacitances, you're really starting to push the envelope with using alligator clips. Okay. But this is pretty impressive. Now let's just demonstrate very quickly a couple inductors. So let's go over here to the 300 microhenry scale, and the way that you do this now is you short it out and then 0 meter. Okay, there we go. And we're going to do a very similar thing with our alligator clip. Okay. And this is measuring about 90. So is that right? We have, yeah, about 90 microhenry. Now this is labeled a 100 microhenry inductor, but let's see what the DE5000 reads. And it's about 95. Okay. So 95 versus a little over 90 on the 300 scale. But let's now go to the 100 scale. Looks like that's zeroed. And test this out. And look at that. We are reading between 90 and 95. So approaching 95. Pretty good. And then finally I've got an inductor that is labeled 10 microhenry. So let's go down to the 30 scale. zero this out here. A little bit more touchy on that scale. All right. And on the 30 scale, I'm reading 10. Bang on. Let's move down to the 10 scale and just see what I get. So I've zeroed out. Good. And in fact, I'm getting just a hair under 10. All right. Let's drum roll, please. Let's do the DE 5000. And I'm getting just a hair over 10. So this is in the vicinity of 10 microhenries, maybe 10.1. Maybe closer to 11. I'm sorry, 10.8. So there we go. I'm inclined to declare victory on this. Maybe a couple little things I want to shore up inside mechanically. But there you go. This is a very nice little meter. I'm very pleased that I got it. So I'm quite fond of this, and it will probably make appearances in future videos. I hope you found this interesting and useful. If so, please give it a big thumbs up below. And as always, thanks for watching.